Welcome to class today, Electrical Engineering 362. We're continuing our discussion on Module 3 regarding single-phase transformers. If you'll notice in the handout notes that I posted up on Canvas, these notes have been revised. I have added a numerical example from the no-load test. And I want to summarize now what it is we got from the no-load test. And then you can go back and refer to those notes again if there's any questions. And we're going to continue for a little bit with the no-load test and then with the short circuit test so that we can understand how you can find all of the parameters for a transformer by measurement. As we described last time, we talked about performing a no-load or an open circuit test. And with that test, we had the single-phase transformer with the primary winding, secondary winding, the core, and we were able to measure, in addition to the primary voltage and current and the secondary voltage, the input volt amperes, which would simply be the product of V1 RMS times I1 RMS, and assuming that a power meter were available, we measured the input power factor. And this would have been sufficient for us to find, or at least estimate, the magnetizing reactance and the core resistance. Now, in performing this power measurement, we recognize that what we have is, since we could measure the input power factor, we know that this angle here, if we're looking at a phasor of the powers, phi sub c, would be equal to the negative of the input power factor. Here is the volt amperes, and along the real axis we would have the core loss, and along the imaginary axis we would have the magnetizing reactance. We recognize that we could have just measured instead the power and the volt amperes. If we did that, then cosine phi sub c could be found as the ratio of the input real power to the volt amperes. We were also able to calculate from this test the exciting current, or I like to call it excitation current, because while some people find this exciting, it just doesn't sound right. So the excitation current, the no-load power factor, which is assumed to be lagging. From there we could find power factor angle. With that power factor angle, we come up with the excitation current. Now this expression here doesn't use a power factor angle, it uses phi sub c. But we recognize that there's a negative conjugate relationship between these two angles. And so that's why we have this negative sign right here. And that would make sense because we have a inductive load represented by this expression here. And what we're after really is from these current measurements and the power measurements, we have this parallel branch that has a resistance associated with the core loss and a reactance associated with the magnetizing current or magnetizing VARs. We also recognize that the direct measurement of voltage and current from the primary side gives us an approximation. It's not exact. The reason for this is that we still do not know the primary side resistance and leakage inductance. And so in calculating the values of X sub M and R sub C from the open circuit test, we're neglecting the impact of these two parameters here. But they will have a pretty negligible effect on the results. And we could prove that to ourselves if we wanted. Let's take a look at this open circuit test from a little different perspective now. First of all, notice that what I've got here is a different core structure than what we have been talking about. This is called an EI core structure. It's the most common core structure that is used in the building of single-phase transformers. And with the EI core structure, you usually have a laminated cores structure where the laminates consist of an E shape. And notice that the middle leg is exactly twice as wide as the side legs. And then it's pressed together with a bottom I lamination piece here. And then you wind the primary and secondary windings around the middle core, as is shown in this picture. You could understand a little better what is happening here if you looked at this from the top view. And you would have, the way I'm showing it, I've got a primary winding wrapping around the middle leg, and then right on top of it I have a secondary winding, and I'm representing multiple turns and showing here that I'm bringing out the ends of the winding from the secondary side here on the right, going out and going in from the primary side on the left. If you zoom in, you can see that I've got the primary side currents going into the paper here, and this is like I've just kind of taken a cross-sectional cut of a view of the windings. The current of these little X's right here, just trying to emphasize going in and then coming out on the other side, and then you just wrap around here like that. And if you have a current in that primary winding, you would get a flux in this direction in the middle core, and then that flux would split up and it would go out to the two sides. If you actually had current flowing in the secondary winding, then what I'm showing here is I've got that current going in on the left-hand side opposite and coming out on the right-hand side. So it's actually like this is the start of the winding here. This is the end of the winding right there. And the result of that would be to create an opposing flux in the other direction from the secondary windings. Just wanted to make that clear to everybody first. Now we're going to consider a test, an open circuit test, on a particular core structure consisting of M5 steel 0.012 inch laminations. And this is very similar to an example in the book, and it's also referred to as M-5 grain-oriented steel. That has to do with the way it is manufactured, and usually grain-oriented steel is lower loss steel. And what we're going to assume here is that we have a catalog containing the data sheets having the information that we would need to analyze what we are getting under an open circuit test, and to use the measurements on this structure to derive our magnetizing reactance and our core loss resistance. So let's talk a little bit about this particular transformer. The transformer has primary side turns 165, and it has secondary side turns of 55. We have core dimensions, which are indicated in this picture here. We've got the middle width, which is a critical parameter. The rest of the widths of the core structure everywhere are half, exactly 1/2 of that. We have the core height, total height, the core total width, and the core length or stack length. And this is a little different way than when I first introduced it, of looking at the dimensions. So you can have the dimensions presented to you in a number of ways. So don't get tripped up by this. If, for example, you need to calculate the magnetic length of the core. So in this particular example, I'm going to write down the dimensions that we have given us. So the width is 6 centimeters. The length, physical length, is 3 centimeters. The width of the whole structure, which I'm calling D, is 14 centimeters. And the height is 10 centimeters. Since we have laminations, we have a stacking factor, K sub S, and we will assume that that is 0.94. There's another piece of information that we're going to need, and that is the mass density of the steel. So mass density of steel is 7.65 grams per centimeter cubed. We also have given to us in our data sheets a number of curves associated with this material. This curve here on the right shows us the excitation volt-amperes per kilogram. Now this comes right from the book, and he says it's called the exciting volt-amperes. So if you want to call it that, that's fine. Notice that it's in VA per kilogram. This is intended to be a general measurement. Often when someone designs a transformer, the one variable that they can change is the length. So if they want to put more flux into the core, they might just make this core longer. But note that the laminations that we've picked here, as we're showing, those are fixed in size. So the length is just how many of them that we are pressing and stacking up together. Hence, we typically refer to the length in a laminated core as a stack length. On the right, we have a core loss curve. I'm using a lowercase s sub phi and p sub c for these things. we are assuming with this application here, this setup, that we are operating at 60 hertz excitation. We'll go into the rest of the information later. Another important thing that we can use is the BH curve. So we have here on the y-axis a B in Webers per meter squared or Tesla, and we've got the H in ampere turns per meter. This is also referred to as a DC magnetization curve. But what does it really give us? It gives us that can be confusing, but remember that you can use these core structures with DC inductors as well. But with AC excitation, B that is on the curve is proportional to the peak of the voltage that is measured as a result of the flux, the time derivative of the flux linkage in that core. So what we're really looking at here is a B peak value if we were to associate the quantity on the y-axis with an electrical voltage. If we want to associate this quantity on the x-axis with an electrical current, we really can think of it as an H peak. Okay, so what we're after now is to find two things. We want to find the magnetizing reactance and the core loss resistance. We talked about it in our last lecture already without a numerical example, but in the handout notes I added a numerical example already. We're just looking at finding it a different way. We also will use the core loss to make an efficiency calculation. So the first step, step 1, find the core flux density. Now I failed to mention that we're going to consider the same basic measurement and transformer rating that we considered in the numerical example in last lecture handout notes. So what we have is we have a transformer with the VA rated equal to 100 volt amperes and primary side rating equal to 120 volts. So we're going to perform this no-load test by turning this little knob here, which allows us to slowly increase and build up the voltage for our test. We're going to increase it until our little needle moves up here, and we measure voltage on the secondary side that lines up with us seeing, and let's assume that we've got a meter measurement over here. So the power supply also tells us what voltage we're getting, and it says, okay, I've got V1 120 volts, and then I'm going to say, what is V2? What's the secondary voltage that I'm seeing here, the RMS value for that? So what we're going to do is we're going to use this very, very important equation that I introduced to you earlier. The EMF, electromotive force, is related to the flux density in the core in this way. Square root of 2 times pi times the electrical frequency times number of turns times the core flux density times the area of the core. And then because we have laminations, we would have to multiply that area times the stacking factor. In this case, we're measuring the RMS voltage on the secondary side, V1. In this test, we're measuring the RMS voltage on the secondary side, V2. And since this is a no-load or open circuit test on the secondary side, the voltage we're measuring is exactly equal to the voltage across the coil, E2. And that voltage that we measure in this test ends up being 39.56 volts RMS. We can then find the flux density rearranging the top equation. Now the turns here that we're using, since we're making this measurement on the secondary side, need to be the secondary turns. We also don't directly have the core area, but we can find the core area. The core area would be this W here times this L. W times L, and then we have the stacking factor. So we plug in what we know. We've got 39.56, 6 times 3. Now it's centimeters. Remember that we have to convert everything into meters. So we're going to multiply times 10 to the negative 4 to do that, times the stacking factor on the bottom. We end up with a core flux density of 1.59 Tesla. Now this tells me that we've done a good job of coming up with a good, example problem, because if we look at our curve, it is placing us pretty close to the knee. Now, because we know this core flux density, we can go back, look at the other curves in our data sheets that we have been given us. We have the excitation, volt amperes, and that's on the x-axis. So here's the flux density on the y. Let's find 1.6 or 1.59, close to 1.6. Draw a line over till it intersects, and we come down here, and what we end up with is we have 2 VA per kilogram at that flux density point. Next, let's look at the core loss. We find our flux density, 1.59, draw a line, we hit this curve, come down here to the x-axis, and we've got 1.8 watts per kilogram. Now, in order to actually find the watts associated with the core loss and the volt amperes associated with the excitation volt amperes, which is what we're going to need to find the core loss resistance and the magnetizing reactance, we need to find how much that core weighs. We need to find the core mass. We would first find the mean path length through which the flux is flowing, or that is associated with the magnetic field intensity in the core, which is, because of this core being the way it is, having the width with twice as much as the side and the top. Whenever it hits its peak, it'll be the same flux density associated with that peak everywhere in this core. And we need to find the magnetic path length. And I did this example specifically so that I could show you how to look at a different core structure. We've got these two windings, and we've applied our right-hand rule. Figured out, as I explained earlier, the primary side is winding, N1 is producing a flux in the direction of this arrow. If we're running an open circuit test, there's no flux associated with the secondary winding, but that flux is dividing up in half and flowing through the other side, taking the flux right, assuming right in the middle of the core. That is the flux will be associated with the core magnetic field intensity distributed throughout this core. We're going to find the lengths of all these paths. Total length would be the laying core on the left-hand side plus the length of the core on the right-hand side plus the length of the core in the middle. We know that the dimensions, this is W over 2 on the top. On the side here, it's the same. The height, H, that was 10 centimeters. The total width here, 14 centimeters. This width in the middle is 6 centimeters. And then the stack length is 3 centimeters. The length of the left-hand side is going to be adding up these distances here. So that comes out to be 2 times half of the total width, which we call D, subtracting off of that half of this width here. So we're calling this W over 2. This is divided in half because we're only going to the middle point right here, and that's something that we could make a small mistake if we're not careful. H minus, we have W over 2 on the top, W over 2 on the bottom, but we're going halfway in the middle, W over 4 and W over 4. That becomes W over 2 total. Okay, so that is LCL, identically the same on the other side. And now the middle is simply the height. And everything will simplify down to this. Okay, so from we can plug in everything that we have. I'm going to leave everything in centimeters right now. I'm not going to need to convert this to meters. And so my final value ends up being 47.5 centimeters. That's the total mean length of the core. Now the volume then is simply the length of the core times the area of the core. Because we have laminations, it is appropriate to use the stacking factor because that would reduce the weight, because there's effectively some air in that physical space for the area of the core. And so we have L sub C times W times the stack length L times KS. We're going to leave our volume also in centimeters squared, and the volume is 803.7 centimeters cubed. Since we have our mass density, we can find the mass of the core. It's going to be the volume of the core times the mass of the core, 803.7. And then remember that we had provided to us the mass density, 7.65 grams per centimeters cubed. We're going to want to convert that to kilograms per centimeter cubed. And our final mass is 6.15 kilograms. And now that we have this, we can quite easily find our excitation volt-amperes. That's going to be this little s sub v times the mass of the core that we found earlier. Recall it was 2 volt-amperes times the mass, 6.15 kilograms. And so our excitation volt-amperes is 4.3 volt-amperes. And our core loss, 1.8 watts. Our core loss is 11.07 watts. And now we can quite easily find our X sub m. It is going to be E1 squared divided by the magnetizing bars. So how do we find the magnetizing bars? There are two ways that we could do it. We could say that Q sub m is equal to the square root of excitation squared minus P sub C squared. Or we can do it another way. This is the fastest way. But we could also say that the cosine phi sub c is equal to the ratio of p sub c over s sub phi. We could find phi sub c is the inverse cosine of p sub c over s sub phi, and then the reactance would be equal to. So either way gives us the right value. Let's use the easier one, and that ends up being 5.36 VARs. Obviously, we've got a lot more core loss now than we have magnetizing reactance in this particular situation that we're considering. Remember, when I did the notes, I assumed that this cosine of phi c was 0.6. What is it here? Well, let's find out. Cosine of phi sub c is equal to 11.07 divided by 12.3, and that is 0.9. So we have almost unity in this case. It looks like it's almost all resistance, and the example in the written handout that I gave you was more evenly divided with the cosine phi sub c of 0.6. We need to know one more thing. Do we know E sub 1? Well, in this handout example that I gave, we could have used V sub 1 and ignored the leakage inductance. Here we have a direct calculation, though, of everything, because we've calculated the P and the Q from the actual physics and physical characteristics of the core, and we've directly measured the secondary winding, V2. That's equal to E2. If we refer E2 to the primary side, we get E2 prime. That would be equal to N1 over N2 times whatever we found as E2, and E2 prime equal to E1. So E1 is equal to 165 primary turns over 55 times the measured E2 value that we found. So our E1 ends up being equal to 118.68 RMS. And our X sub M is that value squared divided by Q sub M. Finally, X sub M is, so it's 1.27 kiloohms. There's one more quantity we can find that might be helpful and insightful, and that is the excitation current. So we can find the magnitude of the excitation current. That would be equal to the value of excitation volt amperes divided by the V1 that we're measuring on the primary. Recall that we had 120 volts on the primary in our test setup. And so that is going to give us 12.3 volt amperes divided by 120, and that gives us 102.5 milliamps. We also know that the excitation current, the entire phasor representation of it is this expression, So the inverse cosine of 0. Okay, so that's our angle there. And I'm going to go ahead, I've calculated the polar form of it because that's usually what we're going to use. And we already know that it's whatever we would call the power factor angle. So remember, without having to calculate it, because we've already found phi sub c, that's equal to negative of the power factor angle. So it's negative 25.84 degrees. So we have everything that we can get out of our open circuit test. Now let's go on to the short circuit test. We're going to use the short circuit test to find the rest of the parameters that we need. Well, so far we've been able to find this magnetizing inductance, the core loss resistance, but we still have these other parameters that we need to find in order to fully characterize the single-phase transformer. So we've got XM, RC. We need to find R1, XL1, the XL2 secondary leakage inductance, and secondary resistance. Now we can perform a short circuit test as shown here. Inside of the yellow box, of course, is the transformer. I'm showing, as I did before, that we're feeding this from some kind of a source. Again, it's probably a variable source. There's probably some impedance upstream of the transformer. It's not negligible, but since we know the voltage, if we can measure it right there at the terminals of the transformer, and if we can measure the current right at our short circuit test fixture, and if we can measure the power factor looking into the transformer, we have everything that we need. So from the short circuit test, our meter on the primary gives us a primary voltage of 115.2. This is just a number I made up. I'm assuming that you're drawing a lot of current during this test, and it's maybe giving us a bit of a voltage drop across this impedance up here. Maybe we've got a low line, whatever, it doesn't matter. I just made it different just to show that it can be different. We're still looking at the same 100 VA rated transformer, 120 volt rated on the primary side. We know that we have a turns ratio on this transformer of 3. We found that in our last lecture using this same example. We also are able to measure the input power factor, and it's quite low, 0.2. Under this short circuit condition, it's lagging. And then finally, we can measure the current on the secondary. That's the short circuit current. So I'll put a little underscore SC to indicate that. It ends up being 27.5 amps RMS. Now I'm going to draw the equivalent circuit we're going to take out the transformer symbol, and this is the equivalent circuit that we will be using to analyze transformers from this point on. So the equivalent circuit, we've got a voltage applied. I'm going to ignore that feeder impedance, and I'm just going to say that this voltage right here is the voltage that's applied to the transformer. This is R1. The leakage reactance on the primary side. The magnetizing reactance. The core loss resistance. The primary referred secondary side leakage, XL2 prime. Primary referred secondary side resistance, R2 prime. We have a short circuit for the short circuit test. This would be I2 prime, the short circuit current referred to the primary. We have our V1. We will assume it's referenced to 0 degrees. We've measured a 115.2 volts at 0 degrees. We have our core loss resistance, our magnetizing reactance. We found these two values already in the previous test. Now what's interesting here, because we're operating under a short circuit condition, the current into the short circuit is going to want to flow in the path of least resistance. So it's generally not going to want to go down through this magnetizing branch. Therefore, it is quite reasonable for us to neglect it. So we will basically assume it's not there. If that's the case, then the current from the input side, I1, ends up being equal to the primary referred short circuit current. And what is that? We know that to refer the short circuit current of the secondary side to the primary, we would multiply that current times the inverse of the turns ratio. So the current seen from the primary side is 9.2 amperes under the short circuit condition. You say, oh, I shorted the secondary. Why isn't it really high? Well, this is a fairly low rated transformer. And in reality, what is happening is that these impedances are limiting that current. And we'll find out that they're quite reasonable. So we know the current of the primary equal to the full phasor form of the primary referred current is 9.2. I'm just going to call this I1 short circuit, and negative 9.2 at negative 78.46 degrees. So from that we can find the short circuit impedance. It's the ratio of the voltage on the primary to the current. This is the short circuit impedance looking in from the primary side, and that impedance is 12.5 ohms at an impedance angle of 78.46. So remember from Module 1, this is what we were calling a magnitude of an impedance, and this is what we were calling a impedance angle, which was the negative of the power factor angle. Now the short circuit impedance is the impedance of this whole branch right here. It would follow then that the real part of this short circuit impedance is equal to R1 plus R2 prime, and the imaginary part is XL1 plus XL2 prime. Now what we need to understand from here is how do we find the individual values of R1, R2 prime, XL1, and XL2 prime? Well, we could, if we do not have any more information than this, we would have to make an assumption. So one assumption that could be made is that R1 equals R2 prime and XL1 equals XL2 prime. It's actually quite reasonable to make this assumption. We could go through and prove that to ourselves if we have a pretty symmetrical looking coil structure, which we do. If you recall, we're still talking about this particular structure right here. So if this is true, XL1 is equal to the imaginary part of the short circuit impedance divided by 2. So what we have here now is the equivalent circuit, including the transformer symbol, which is right here in the middle. And if we're going to show the parameters the way that they would be physically measured from the primary side or the secondary side over here, then we would have to represent it this way. It's really kind of inconvenient and makes it difficult to solve problems, though, if you use this circuit. That's the reason why we do the transformations to the other side. So what we would want to do is we would want to take all of the parameters and the currents, voltages, when I say parameters, I mean the impedances, and move them over to one side or the other so that we can be looking at everything from either a primary referred, right, or a secondary referred perspective. That's the first thing we need to be able to do. So this circuit here shows all of the parameters referred to the primary side. Notice I'm showing that the impedances have to be multiplied times the square of the turns ratio to move them to the primary side from the secondary. So for example, in general, Z prime would be N1 over N2 squared times the, let's just write Z2, so it's a secondary side impedance, referred, and then the actual impedance Z2. And when it comes to the current, we would be dividing by the turns ratio. So the I2 prime would be N2 over N1 times I2. If we were using a turns ratio, it would be an A squared. For the impedance, an A. For the current, 1 over A. What about voltage? We didn't really show that. I left it off here. Go back to this original circuit here. There's a voltage right here. So this is V2. Then we would have to have V2 prime, and the V2 we'll put over here the voltage to the left. That would be just multiplying the secondary side voltage times the turns ratio. So then we can take this circuit right here and simplify it, and now we've got all of the primary side parameters. I'll just list them. We've got XL1 is 1.17 ohms. I'm sorry. We've got R1, XL1. These are all ohmic quantities. Just want to make a little bit of correction here. I flipped some of the numbers, had a little bit of dyslexia going on here. I had 5.16. It was 6.15 here. Just in case anybody's confused looking at these numbers. Okay, so I've now written down all of the parameters referred to the primary side. We'll just start with that, and we can start to look at an example of, let's say, where we put a particular load on, and we can start to look at currents and voltages. So, for example, we might have a problem that says I have this transformer, and it's rated. When I use ratings, I typically put a little subscript R. So the rated VA, that's the same as the rated apparent power of the transformer, is 100 volt amperes. The rated voltage on the primary side is 120 volts. We know that the turns ratio is 3, and so the secondary side rated voltage would be 120 divided by 3. So that would be 40 volts. So those are some ratings, and we're going to actually come back and look at why those are used. Sometimes you might have a problem where you're given ratings and you're not asked to use them. If you can't see how to use them, then maybe you're looking at half of the problem, and this is what you see in some of the book examples, because later on they will use the ratings for per-unitization, and I'm going to review that quickly with you. But anyway, we've got these ratings now for this transformer. and we know all the parameters that I've listed. And let's say that since this system is rated this way, we would assume that we assume, which is really the way, is what you should assume because it's the rating, you would assume that the transformer can supply the rated VA to the load for any power factor. Now let's I'm going to show you an interesting way to approach this, and this is how we'll do most of our transformer problems, not all of them, but we'll say that it is operating at a load apparent power of 100 VA, and let's say 0.95 leading power factor. Now what you're going to look at this problem, and there's really two ways to solve the problem. There's the one that takes 1 page, and there's the one that takes 3 pages. So I'm going to show you the way to do 1 page. The 3-page answer would say, well, I'm going to take this and I'm going to try to come up with the circuit elements for this impedance, and I'm going to use those. But here's another way to do it. What I'm going to say, what's being asked, find the input current and power factor. So we don't even have to know what the load itself looks like. We know that it could either look like a parallel RC, or it could look like a series RC. But we don't care because we know what the apparent power is going into the load. So if we know the load apparent power, we can find and the power factor of the load. I'll put a PF seen from the load. And then what we can do is we can solve this problem by finding the secondary current first. We can solve this all referred to the primary, and we'll have to assume the secondary voltage is your reference. What that would mean is, now one other thing is I didn't say the voltage, so we would have to also say that it has a load voltage. So V at the load, let's say that V at the load is our rated voltage of 40 volts RMS. Then V2 prime would be 40 times the turns ratio at 0 reference angle, because we're defining the power factor from that point. So that's essentially 120 0 degrees. The other thing that we would need to do here is to find the load current, which we could. In fact, we could find the whole load current phasor. So load current phasor would be S of the load divided by the V of the load at the power factor angle. We know that it is a positive angle because it's a leading power factor. So we would say inverse cosine of the load power factor. And so we have 100 divided by 40, and we have to find the inverse cosine of 0.95. And our resultant current then at the load is 2.5 amps with an angle of 18.19 degrees. There's one other thing, though, that we would have to at least assume to solve this problem. I said that we need to find we're asking to find I1, and we're working the problem back from the load. The question now is, can we actually find everything working back from the load? Yes, we can, but we have to apply some of our circuit knowledge from our early circuits classes. Since we know the current at the load and we have an equivalent circuit, we can find the input current. And that input current will, in order to do that, we first of all, let's reflect the secondary current to the primary. So I2 prime is going to be 2.5 divided by 3, which is 0.83 amps. If we know that, then we can use a current divider to find I2, or to find I1. So let's look at a part of our circuit. We have I1 coming into a node. We have a parallel branch here of XM and RC. And we have I2 prime here. Now, I have to take back one thing I said. In this problem, to solve the problem, we actually would have to find the reflected load impedance. If we didn't have to do this current divider, we wouldn't have to do that at all. And you'll see that sometimes if we assume that this part has a very large impedance, it is a very simple problem. We don't have to even find the load impedance. But it looks like we're going to have to do that. But we can do that, right? So there's one thing here too that we cannot forget. We have an impedance in series with the Z load, which is associated with the transformer. That would be the R2 prime plus JX L2 prime. So we can do a current divider to find I1. Let's just, for the moment, simplify what we're talking about and combine these two impedances here. And let's call that, we'll just call it Z2 prime. And we've already decided to use this, to call this ZM. And the current divider tells us that I2 prime is equal to I1 times ZM over ZM plus ZL. And we can simply rearrange this and find I1 as ZM plus ZL over ZM I2 prime. Now it's costing me a lot of my own time to go through this math with you, but I'm going to just show it to you so you can see an efficient way to do it. So hopefully you're grateful for this because I'm paying a heavy price for it. Anyways, you will need to be doing this kind of thing in the homework. Let's first of all, we're going to remember that we need to have things in polar form to do multiplications and divisions. If you try to do those in Cartesian forms, then it's just a math mess. Don't do it that way. To do addition, you want to put everything in Cartesian form. Okay, Cartesian form, going from polar to Cartesian cannot be avoided if you're in polar form. So this is probably where it is going to take your time. Okay, so that would tell me that I'm going to probably want to have these impedances I'm interested in here. Before I'm done, I'm going to be doing some additions and some multiplications. So we already have, we can find ZM. It's the parallel combination of these two branches of impedances, RC and XM. So we should probably come up with a polar and a scalar form of this. So that is on the top, I've got polar. I'm going to have to convert the bottom to polar. To do this efficiently. So I'll remind myself of what these values are. 2.6K, 1.3K. So that is 2.6K times 1.3K. And then the J is 90 degrees. Actually, this isn't quite in polar. It also has to be converted. It's easy though. And then this is 1.3K plus J 2.6K. And I need to convert this to polar. So I got to square these. And I've got to take the inverse tangent of 2.6 over 1.3. So this becomes 2.9 63.4. And now I'm gonna, so the denominator is simplified to that. So I've got 2.6k over times 1.3k over 2.9k, 90 degrees minus 63.4 degrees. I know I've done it right because I've got a positive angle because it's a lagging load. So I have 1.17 kiloohms with the angle of 26.6 degrees. I'm going to want to convert this to polar, to Cartesian. So there's your polar. Let's make our Cartesian. That's going to be 1.17k cosine 26.6 degrees plus j 1.17k sine 26.6 degrees. So there's my polar, or my Cartesian version. And now we've got to do Zm plus Zl. We've got a Cartesian version of Zm. We need to get a Cartesian version of Zl. So recall that Zl, did we find Zl? Oh, we haven't found it yet. Okay, so Zl, it's actually Zl prime. Let's make sure we've got the primes in here. This is, got to go back and fix this. This is Z2 prime. 2 prime. So we got a little bit of work ahead of us here. We've got to find Zm plus Z2 prime, which is Zm plus a Z load prime plus R2 prime plus JXL2 prime. So we've got to add all those things up. Now the Z load prime, it's not too hard to find. Z load prime is V2 prime divided by I2 prime. So we've already said that it's 120 volts using a reference angle of 0, and I2 prime is 0.83, 18.19 degrees. We have a leading load. So the Z load prime is this. In polar, let's put it in Cartesian. I'm not going to work this for you. I'm just going to calculate it. You can fill that in yourself if you want here. Okay, we are going to be able to do this calculation here. So we have Zm plus Z2 prime is 1.05k plus J520 524. There's no K right here. Plus the Z load prime plus R2 prime, which we remember is back up here, 1.34, and XL2 prime is 6.15. Okay, so we'll simplify all of that. Add together all of the real values. So we're going to add these guys together here, and we get 1.166, and then we're going to add the imaginaries together. We've got that value there. We should probably convert it into polar. So we're going to go back here and look. We've got a Cartesian version of ZM, a polar version of ZM, a Cartesian version of the sum of these impedances, the polar version. I'll put it down here. I'll let the diligent student check my math. Oh, and by the way, this is a kiloohms here. Okay, there we go. Now we can, what do we need to do? We need to use polar forms of this. So let's use those. We're going to use the polar form of ZM and the polar form here of ZM plus Z2 prime. And we're going to find I1 is equal to ZM plus Z2 prime over ZM times I2 prime. That's 1.247 over 1.17. Now these have a K, they're 1,000, but that's going to cancel. The angles, we can multiply this times the current amplitude of I1 of I2 prime. What was that? I2 prime was 0.83. This makes sense. I'm feeling good about this so far because more current needs to be supplied from the primary side because of the need to supply the magnetizing current down here. So I expect I1 prime to be larger than I2 prime. What about the angle? So I've got the angle of ZM plus C2 prime here. That's on top, 20.74. I'm going to subtract the angle of ZM, which is 26.6. Notice that this is going to be less than 0. And I have one more angle. It's the current of the load, which was at an angle, a positive angle of 18.19 because it was a leading current. I'm feeling good about this because this tells me that the transformer's going to make it more, it's going to make it less leading. Okay, so let's simplify that, and now we have I1, which is 0.885 amps at an angle of 12.3 degrees. So it's leading, but not as bad, not as badly leading. So there's your primary side current. we could, in fact, find the primary side voltage if we wanted. Okay, so if we were going to find the voltage, what would we do? Well, let's look at what we know. What we're saying, because we solved it from the load side, is that the voltage applied to the primary has to be dependent on whatever we supplied to the load on the secondary side. So V1 becomes a variable that we're going to calculate. It's going to be larger than what was applied across the magnetizing voltage, for example, by the voltage drop across R1 and JXL1. Now we could solve this a couple of different ways. Probably the easiest way would be to acknowledge that we've got our magnetizing branch here. So, and we already know the current here, and it's different than the current here. We've got a drop across the secondary side impedances. And we know that our voltage on this side of the load, we know what it is. It's a V2 prime, right? So that is equal to 120 degrees at an angle of 0. Your reference angle doesn't always have to be at the source. It's where you'd use the power factor. And then we'd have a new power factor, which we've already found looking in here, right? So the power factor looking in here is going to be the cosine of 12.3 degrees leading, because it's positive. So that's the input power factor, or on the primary side, we could say PF1 is equal to 0.98. It's almost a unity power factor, but not quite. It's got a little bit of leading to it. So there's that input power factor that we wanted to know. And now we can find V1. And that is simply going to be V1 is equal to R1 plus JXL1 times I1 plus R2 prime plus JXL2 prime times I2 prime plus 120. Okay, there you have it. Now, okay, am I going to be a nice teacher and do this? I'll just, I guess, let me show. I'm going to really regret this, but I'm going to do it. We know that the R1 was 1.17 plus J 6.15, I1 prime 0.885, angle of 12.3 degrees plus 1.34 plus J 6.15 times 0.83, angle of 18.19 degrees. And we would just solve this. what would you do? Okay, you're going to convert this to polar, so you can do a multiplication, and then you're going to convert back to Cartesian and add everything up, and then back to polar again. So I'm going to say, I'll do that. Okay, so far so good. Let's multiply these guys out. Okay, so on the primary side, we're going to have a voltage drop of 5 point. Remember that we have to add 120. This is 0 degrees. Don't forget that. People always make that mistake on tests. Okay, there we go. Now I have to convert this into Cartesian. And I can tell you that there are exam problems that'll be similar to this that may not be so they wouldn't be this time consuming, but definitely you're going to see some of your homework problems are a little bit more challenging. Now, one thing to notice that because this is greater than 90 degrees, we're going to end up with a negative real part of this. So the cosine will be a negative number, but the sine is a positive number. We've moved into another quadrant. That's why the same thing's going to happen here. And this makes sense because we're talking about a voltage drop, right? And I've actually taken into account all of that. No, it doesn't make sense. This is looking a little bit weird because we would expect that we're going to have a voltage increase, but we have a leading power factor. So that's why we've got a kind of a weird result here. So let's just go the rest of the way and see what we end up with. So this is very interesting. The real component of the voltage is going to be negative. And let's see what happens. This is because we had a leading load. And so I'm going to add up all of the real parts. So it's a little bit lower on the real component here, but not by very much. And then let's add up all of the reactive parts here. Okay, so that's the voltage, but let's get it into polar form. Okay, now this is weird. It makes me think I've done something wrong, but maybe not, because there is such a thing as voltage amplification that comes when you introduce a capacitance with an inductance. So maybe I haven't. So I was just, trying to make this interesting, and I've kind of opened up a new can of worms. But I think this is right. And if you want to check this, if you're interested, go ahead. It's a little bit of a deep-ish thing to explain as to why my voltage on the primary would be lower than the secondary. But what it is probably is some kind of a resonant point at the fundamental frequency of everything that could give you. Okay, so there you go. What we're saying in this case is that I've got a primary side voltage applied to this thing. This is the transformer. I'll just show it as a box with the turns ratio shown this way. And then we've got a load that has it's a leading load. And this is the voltage across the load. And if I move it over to we're basically saying we moved everything over here, and it looks like this, where we have some inductive impedance here of the transformer. We've got the load, and it actually, because it's leading, is going to be somewhat capacitive. And the fact that we have V1 less than V2, this is V2 prime, why could that happen? Well, if you had a purely inductive voltage, you had something like this, and you had V2 here. This is for the interested student. And if you plotted the ratio of V2 over V1, the ratio of those two would be, this would be 1, but there'd be one frequency where it might go higher, and then it's going to start to roll off at say a steep slope. I'm not going to get into log because this is not, it's really 40, it's minus 40 dB per decade, but this is not part of the class. Anyway, at this point, V2 is higher than V1. That could be what's going on right here. It's quite common. In fact, it happens in induction generators. This is the principle upon which induction generators work, and we do not cover induction generators in this class. They're very, very complex animals. So very, very nice. Now, there's one more thing that I have to, two more things I have to teach you. Okay, so we've got two more things. Number one, efficiency. What is efficiency? Efficiency is defined as P out over P in, the real power out over the real power in, and usually it's given in percentage, so you multiply it times 100 and put a percent sign in front of it. So let's look at this example up here that we have. What is the output power? I'm going to go back. We've done all this math. I'm going to go back to this guy right here. We've got our load. The load is the output of our transformer. It's got an apparent power of 100 VA and 0.95 leading. We know that we can find the output power quite easily. So the P out is going to be equal to the load apparent power times the power factor at the load. So that's 100 times 0.95. I don't care if it's leading or lagging, that's what it is. It's 95% of the volt amperes is real power. So that is 95 watts. What is the P in? We can find the S in, can't we? The S in would be the S supplied to the primary side of the transformer, right? What is that? That would be V1 times the conjugate of I1. So V1 we found, for better for worse. Now if this efficiency ends up being more than 100%, I've made a mistake. So let's check here. We've got V1 of 119.78. It's almost 120. Okay, now here's the interesting thing. We have an angle here, right? So we have to use that angle, 5.14, and then we're going to multiply it times our current, but we have to conjugate the current. So the I1 we found was 0.885 with a 12.3 degrees power factor angle. I'm going to make it negative 12.3 degrees. Okay, so let's find S in. Okay, there's our input apparent power. Remember, we've got it looks leading, makes sense. We've got a negative angle there. It's what we expect. Now the power factor is going to be the cosine of this angle here. So the input power factor, well, we already found, well, we're just going to do this. It gets kind of weird here. So I'm going to go back here. This is not incorrect. That's not the power factor. Why? Because this was not referenced at 0. Okay? You have to have a 0 reference for this to be the power factor, so I was incorrect with this statement. Nothing else is based on it so far, really. We're finding the true power factor right now. This is strange, okay, because what we're really seeing is, let's go back here before, the cosine of 12.3, that was a small number. Okay, we're good. So we're going to take this. It's the cosine negative 7.16. The input power factor is 0.99. So it's almost unity. The transformer is almost compensated for the leading load, which really does tell me that this gain is probably happening here. Okay, now I know that I can find the Pn. Pn is equal to 105.17 watts. So the efficiency in this case, and this is the symbol we use for efficiency, is the P out over Pn. Let's leave off the percent. It doesn't have to be in percent, but we can just be in a per unit looking thing. So that is P out 95 divided by 105.17. So the efficiency, I'll show it in percent. 95 divided by 107, 105.17, 90.3% efficient. Okay, so I kind of made up this transformer. I'm actually going to go put a box around this formula. You need to know this. Okay, pretty good efficiency. Now we're going to go and do one more thing. We're going to talk about regulation. To do that, we have to revisit per-unitization, which I taught you in Module 1. You have to pick a base, and then you would per-unitize everything. So let's do that. We're going to pick a base of the, we're going to use the primary side rating as a base. Okay, so V base is going to be 120 volts. S base is going to be 100 volt amperes. And we can find I base. It's going to be S base divided by V base. That ends up being 0.83 amperes. And we can find a Z base, which will be V base divided by I base. And that will be 120 divided by 0.83, which is something that's going to look familiar to us because we use the rated power on the output of the transformer. So 144 0.6 ohms. Does that look familiar? Let's go up here to the Z load that we found. I notice I draw bigger the faster I go, right? Okay, so there's our base impedance. We've got all these base quantities now. This is a very key thing you need to know. Now, what are the per unit values? We found V1, right? We can find V1 per unit, and let's see what are we going to use. I'm going to use a little v for the per unit. That's going to be whatever I have for V1 divided by V base. A little I, it's whatever I have for I1 divided by I base. And any impedance that we have, so we could find a little r1, that'll be our per unit r. That will be r1 divided by c base. XL1. I was already using a little thing, wasn't I, there? Let's make it a little different here. XL1 R2 is R2 prime over Z base. Usually when you're doing base, you're just taking your equivalent circuit and you're either doing the base on one side of the transformer or the other and finding the per unit quantities. The XM base, or the per unit XM, per unit RC. There you go. There's your per unitized values, and whatever your base is going to determine what they are. We're referring everything to the primary, so we're using the and we're using the primary as a base. Notice we know that because I'm priming the R2s and I'm priming the XL2. I can also put the load, so I'll put a little load here. CL prime divided by Z base. You never mix and match on each side of the transformer when you're doing per-unitization. Okay, there we go. Now I'm going to show you the quantity with per-unitized values. Show you this circuit. Okay, there is your full circuit with per-unitized values. And there's a couple takeaways here. First of all, if we see that we have 1.0, that means that we're operating at a rated quantity. So we've got, at least because that's the way we're using the base, we're using rated values for our bases, right? That's a rating, that's a rating. It tells me if I were going to design this transformer to supply 1.0 per unit current or 100% current to a load, if I define the rating on the load side of the transformer, at least here for this leading power factor scenario, I would have to derate the transformer. I'd have to actually design the transformer to handle more than 100% load continuously, probably 10% at least, because it's basically saying that I'm at a 7% overload of a rating. So I probably want to derate the transformer. The fact that the voltage is lower again than 1.0, it's because of the weird effect of leading. A student can check me if they want to see if I didn't make a mistake. But it doesn't matter if it's low or high yet. Now we're going to get a bit of a weird answer on regulation, and I wanted to set this up for a regulation, and then we're going to look at a different load and check the regulation out. This is I can give you guys an anecdotal story about how what I'm showing you is a realistic scenario that can happen in class on Thursday. Anyways, this is it. I've gone overtime. I've destroyed my capabilities to be a good researcher by missing a lot of my conference today to give you this. I was so nervous last night I couldn't sleep, so that kind of messed me up. Anyways, here we are, and I hope this is helpful.